Good afternoon, and thank you for joining us today for our webinar, Get the Most Out of Your Database, Understand Indexing. We'd like to start off the webinar today by telling you a little bit about Tokutech. Tokutech offers high performance and scalability for MySQL, MariaDB, and MongoDB. Our easy-to-use open source solutions, TokoDB and TokoMX, are compatible with your existing code and application infrastructure, making our technology an easy drop-in solution without requiring you to rewrite any code. Some of the key things that you can find with our TokoDB and TokoMX solutions are improved insertion performance by up to 20 times, reduced HDD and flash storage requirements up to 90%, and again, no need to rewrite any code. As you can see on our next slide, some of our current customer base. We do encourage you to visit our site, www.tokutech.com, to see how some of these customers, such as Limelight and Mozilla, are using Tokutech currently. I'd also like to go over a few housekeeping rules for this presentation. This presentation will be available for replay following the webinar today, both a video of the presentation as well as the slides themselves. We do welcome all questions. However, we will be answering all questions at the end of the presentation, but please do feel free to ask questions throughout. At this time, I would like to introduce our presenter today, Sardosh Kashyap. He is our senior engineer here at Tokutech, and there is no one better qualified to go over the topic today. So with that, Sardosh, I'll turn it over to you.
All right, thank you, Amanda. So I ought to be unmuted, and I assume everybody can hear me. So if there are any audio issues, please say, I guess maybe Amanda or someone type something now. Otherwise, we're going to begin talking about indexing. So first thing I'd like to do is I want to talk a little bit about just the terminology that I'm going to be using in this talk. I'm going to be talking conceptually about indexing, and I'm going to be using MySQL terminology and language. Even though, I'm sure there are people here that are interested in MongoDB, interested in MySQL, and really the concepts I'm going to be discussing are going to apply to both. But as far as the talk goes, the examples that I give, I'm going to be discussing like tables, not collections. I'm going to be using SQL statements as examples, and etc. But really, mostly everything I say should also apply to MongoDB. All right, so let's begin. First off, what I want to do is I want to just define some concepts. So before we dig into the indexing, let's just make sure that we understand what's going on underneath the covers. We're going to define a dictionary to be a set of key value pairs. We'll assume that you can update the dictionary with inserts, deletes, or updates, and that you can query the dictionary with point queries or range queries. So as an example, B trees and fractal trees are dictionaries, but hashes or things like hash indexes are not, because a range query is not supported. So what's a table? We're going to define a table as a set of dictionaries. So, for example, and once again, just hopefully the last point on MySQLisms versus MongoDBisms, I'm going to be using the term table and not collection here. I might be saying the word column instead of fields here. So a table is a set of dictionaries. So as an example, if you have a MySQL statement of create table foo, A int, B int, C int with the primary key of A, and you insert a bunch of data, you get something looking like what you have over here. I'm hoping people can see my mouse, where you have your rows inserted here in primary key order. Now, the sort order of a dictionary is defined by the key. So for the data structures and storage engines, really what we could think about is range queries on the sort order are going to be fast. Range queries on any other order are going to be slow because they require a table scan, and scanning the entire table is slow. And point queries, which means retrieving the value for one single particular key, that's slow. And I just want to make a quick point here in that a single individual point query is fast, but reading a bunch of rows this way is going to be 2 orders of magnitude slower than reading the same number of rows in range query order. All right, so what's an index? An index I on the table T is itself another dictionary with a defined key value pairs. The key in the index is the subset of fields. In the primary dictionary T, it's the subset of fields that you define, and the value is the primary key in T. And I just want to take a second here to point out when I say the value is a primary key in T, I'm discussing more sort of how InnoDB and TokuDB and TokuMX do it, where the value is a primary key. For something like within my ISAM and MongoDB, MongoDB doesn't technically have the concept of a primary key, so it's not the primary key, and neither in my ISAM. But the point is that the value really is a row identifier into the table T. It is some data that gives you a mechanism for retrieving the entire row. But because for TokuDB, TokuMX, and InnoDB, that's going to be the primary key. So as an example here, if you alter table foo, add key B, you get two dictionaries. You got your first dictionary over here, which is, let's call it your primary dictionary, your main dictionary, the one that actually stores your data. It's sorted on the primary key of A. And in the secondary key of B, you've got your rows sorted by B. You'll notice over here, B is not sorted. It's in random order. In the secondary index, you're sorted by B, and as the value here is you have an identifier that allows you to get the entire row. So for example, if I look at key of B is equal to 43 and I see a row identifier of 412, I know 412 is my primary key, and I can identify the entire row by diving into here and getting the entire row there. So hopefully at this point there is a basic understanding of underneath the covers, given a schema of table and a secondary indexes, in terms of the dictionaries that are underneath the covers, conceptually what the table is looking like. And with that now, I'd like to sort of transition quickly and discuss just a few simple queries given this layout. What does query execution look like? So suppose you have a query of select count star where A is less than 120. Well, this query is going to be pretty fast. What you do is you go into the primary dictionary, you find the rows here that are nice and next to each other where A is less than 120, and you count them up and you get your answer. Similarly, select count star where B is greater than 50, that's going to be fast as well. What you do is you go to your secondary index. Read the rows where B is greater than 50. You have the values of B here, and you count them up. 1, 2, 3, 4. You get the rows, and you're done. When you take this query, select sum C where B is greater than 50. Well, now we got some issues, because what you do, you got two parts of the query. The first part's pretty fast is, well, first you identify which rows are B is greater than 50. And just like the last query, that's a fast range scan over here. Boom, 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 next to each other. You get your row identifiers, 156, 256, 101, and 198. But then now to actually be able to satisfy the query to answer what the sum of C is, well, you don't have C here. You have to do point queries into the main dictionary. And this is why we're saying over here, this part of it slows, because given this row identifier, this primary key, take this 156, I have got to go and do a dive of a point query to get this row over here. And similarly for 256, I got to go and do another dive somewhere completely different in the table. Now, this is just on a little slide here. This is only 8 rows or whatever it is. It looks small, but you can imagine for a big table, this has got to go to a completely different location on your system to get this row. Similarly for 101, it's got to dive here, and 198, it's dive here. So you can sort of see it's like jumping all over the place to get all of these individual rows. It's doing these point queries, and that's slow. So why do we even bother having indexes on our tables? Well, the reason is because we want them to make queries go fast. If you didn't have any queries you didn't care about, then you wouldn't need indexes. Each index is being used to speed up some subset of queries. So given that the purpose of the existence of indexes is for queries, it makes sense for you to pick your most important queries and set up your indexes for those. So the key here is what I'm going to be going through is how to go about designing indexes with queries in mind. And in this talk, I'm going to have three goals. Sorry, I misspoke. The goals of my talk, I'm going to have three simple rules. I'm going to lay out three rules for designing good indexes. And I'm going to do this in a conceptual way that really avoids the details of the data structure that is lying underneath. We're not going to talk about B trees or fractal trees, even though they might be fun to talk about and, do a little bit of math. But all we're going to care about is that range queries are fast, point queries are slow. That's it. The rules that we're going to that I'm going to show for designing good indexes are all about range queries being fast and point queries being slow. But before I get into these rules, it's important to point out that there really is no absolute rule in that indexing is like a math problem. Rules help, formulas help, but really you gotta approach each problem as its own, you just gotta approach each scenario as its own problem and apply problem-solving analysis to it. But all that being said, rules help a lot, and I hope the rules that I'm about to talk about you'll find helpful. So the three basic rules are, I'm sorry about that. The three basic rules are, rule number one, retrieve less data. The less data you retrieve, the less bandwidth you're going to use, the less processing, just things go faster. Rule number two, avoid point queries. As I've said, point queries are slow, range queries are fast. Accessing data sequentially, which is what a range query does, is much faster than accessing data randomly, which are what point queries do. And the third rule is avoid sorting. So we're going to see some group by and order by queries that do some post-retrieval work. You can actually use indexing to help get rid of this work at query time. And with that being said, let's actually start digging into these rules. All right, so rule number one, retrieve less data. And let's set up an example here. So suppose I have a giant table with 1 billion rows and no indexes. It's a simple table, schema, 3 integers, A, B, C. And I have this query that I care about. Select some C from foo where B is equal to 10 and A is less than 150. Well, what's the query plan? We don't have any indexes, so the rows that match this query can be anywhere in the table. And if you don't have an index, you have no way of finding them, so you need to scan the entire table. And this is a very slow execution pattern. You have just scanned, you have processed 1 billion rows just to count 1,000 rows, or just to process 1,000 rows. And that's incredibly inefficient. So what do you want to do? What you want to do is you want to reduce the amount of data retrieved. You don't want to be processing 1 billion rows. So how do you go about doing this for a simple select? And the way you do it is you design your index by focusing on the where clause. It's the where clause that's defining what rows of the query you're interested in. Anything that's not matching the where clause is not important for the query. If you have to process it, you're just going to chuck it anyway. So look at the where clause to try to get that index. And the where clause in this query is where B is equal to 10 and A is less than 150. All right, so let's dig into what we would do. So what index can we use here for this where clause? Well, we have some simple options available to us. Option 1, use a key of A. Option 2, use a key of B. Which is better? And to know which is better depends on something called the selectivity. So if there are fewer rows where A is less than 150, then key of A is better. If there are fewer rows where B is equal to 10, then key of B is better. So really the answer for key of A or key of B, it's data dependent. Which index is better? Which index forces you to retrieve fewer rows? And in fact, there's a third option of you can use the key of A and the key of B and then you merge the results. I don't believe MongoDB has this. MySQL does have this. I'm going to come back and address this option later. So for now, let's just think of options 1 and 2. And the problem is that really neither key of A nor key of B is optimal. Suppose, as an example, you have 200,000 rows where A is less than 150 and 100,000 rows where B is equal to 10. Well, in this case, technically, B is more selective than A, so you're going to want to use the key of B. But still, your query result only has 1,000 rows where both are true. So in this case, both indexes are still retrieving too much data. So one thing you're going to want to do for better performance is you should try to use a composite index. You want your index to try to optimize over as many pieces of the where clause as possible. So we're dealing with composite indexes now with our options. Key of AB or key of BA. Which one's better? And in this case, actually, we could set a definite rule here. The key of B, comma A is better, period. And this actually comes up to something that you can really hold on to, is that when you're making a composite index, place equality checking columns first. I don't care about the selectivity of B or the selectivity of A when I say this. If you always want the equality columns first. The condition on B is equality, condition of A is not, therefore B of A is better. And as an example, so sort of what happens is you see we're really just drilled down on just the rows we care about. Our query is going to analyze just this. It's not going to analyze any row we don't care about. Now, what if you don't have an equality clause in your composite index? If your where clause is where, A is between 100 and 200 and B is greater than 100, what's better? Key of A, key of B, key of AB, key of BA? And this actually comes to a key rule, is that as soon as a column on a composite index is not used for equality, the rest of the composite index no longer reduces the data that's retrieved. So if we're talking about just, as far as analyzing the number of rows retrieved, a key of A is really not going to be much better than a key of AB is not going to be much better than a key on A, and BA is not really going to be much better than a key on B. Now, it turns out in practice, there are corner cases that helps, and recently, at least in MySQL, there's been work done to make these inefficient indexes better. I don't know if people are familiar with index condition pushdown. That's in MariaDB 5.5 and MySQL 5.6. And also MongoDB, I don't think they named the feature. They just sort of, their query planner does some smart things to try to get around these inefficient indexes by skipping over rows in a more aggressive manner that don't match. So I don't mean to just sort of contradict what I'm just saying. I feel it's fair to point out that in the latest releases of databases, there are things to make these inefficient indexes better, but really conceptually, these indexes are still going to be inefficient. So I see someone saying that the audio is breaking up. Is the audio still fine? I'll wait a few seconds to see if someone types something about an audio check. All right, excellent. Thank you. All right, let me take a second to go back. All right, so the point that I was making about inefficiency is, so you take a look at where, if you have this key of BA where B is greater or equal to 5 and A is greater than 150, and you sort of analyze the query, you see this 6,101 here, that kind of snuck into your execution plan if you're just doing a straight scan. And that's the problem. You can get rows where technically B is greater than 5, but A is not greater than 150 will get stuck in. Now, for space on the presentation slide, I only have one row like this, but you can imagine there are going to be a lot of rows. There could be 6.0, 6.1, 6.2, 6.3, 6.4, et cetera, et cetera. And so hopefully you could see why this query plan may, B comma A may not be as efficient as you would think it is. Another example with composite indexes. Suppose you have a where clause of B is equal to 5 and C is equal to 100. This is very similar to what I just said, but you have a key on BAC. Well, that key is going to be just as good as B because A is not used in the where clause. So having C in the index really doesn't help reduce the amount of rows you retrieve. A key of BCA would actually be much better. And as an example, you can see here, you got these rows stuck here where C is not equal to 100, but hey, B still is 5, and they get into the middle of your query. And once again, in theory, these could be quite a lot. And I think this basically wraps up what I was talking about, the rule one of reducing the amount of rows that you retrieve. Once again, just to recap, create composite indexes based on the where clause where you can. Place equality comparison columns first. If there's one thing you want to take away from this talk, it's this item right here. I have seen this really will help your query performance. Make your first non-equality column in the index as selective as possible, because once the first column in a composite index is not used for equality or not used in the where clause, the rest of the composite index isn't going to help you reduce the rows retrieved. Now, that doesn't mean that they aren't helpful. They might actually be very helpful, and we'll see that in Rule 2. And Rule 2 is avoid point queries. All right, so let's go back to an example that I had at the beginning when we were sort of getting our feet wet with query executions. You'll recall we had a table with a primary key of A and a secondary key of B, and we had a query of select sum C from foo where B is greater than 50. And I sort of made the point that key of B is going to be good, but it could be slow because the retrieval cost of each row is going to be high because random point queries are done. And I just want to sort of bring the context back that I discussed at the beginning of the talk. Once again, finding the row identifiers here, 156, 256, 101, and 198, where B is greater than 50, that's fast. But then actually retrieving the row to be able to satisfy the query to get those values of C so you can sum them up, that's going to be slow. And that's going to require point queries into this main dictionary. So what can we do about it? Well, one thing is, suppose instead of using any index, you scan the primary table. And this actually brings up something interesting, about table scans. The primary table is technically the retrieval cost of each row in a primary of a table scan is very cheap. It is very cheap to like the cost per row is small. The problem that you have is that you are completely flying in the face of the first rule, where you are retrieving way too many things, where you are retrieving way too many rows. So I'm actually peeking at the questions. So just quickly, even though I'm going to save most of them to the end, a point query is just a query that retrieves a single row from a dictionary. If you're retrieving a bunch of rows that are together, that's a range query. But if you're retrieving just one, that's a point query. All right, so that's just an example of a table scan here. Once again, this is fast, but there are just way too many white rows that you're going to be reading to satisfy this query. So we want to avoid point queries. How about we add the index of B comma C? Well, since we have an index on B, we're only going to retrieve the rows we need, so that's satisfying the first rule. But since the index already has the information about C, we don't need to go to the main table to satisfy the query. We could just take the information we got in the scan. So we have no queries. You see, you just read these here. You got your value of C sort of straddling along here, so you just add these up, boom, and you get it. This main table is not touched at all. And that is really, really fast. So this brings us to the concept of, I'm sure you've heard, a covering index. This is a concept that, when you hear about best practices in MongoDB, you hear about best practices in MySQL, you really hear about this best practices in databases is the value of a covering index. And hopefully what I'm demonstrating right now is why a covering index is valued. You've probably heard, use a covering index, use a covering index. I'm hoping at this point you understand why you want to be doing this. So a covering index that I'm sure you've heard about, let's define it. A covering index is an index that covers a query if the index has enough information to answer the query. So as an example, if you have a query select sum C where foo is less from foo where B is less than 100, select sum D where B is less than 100. Well, you have an index of B comma C. That's a covering index for the first query, but it is not a covering index for a second query. So a covering index, an index isn't just, isn't like this, isn't going to just cover blindly. It's dependent on what query you're running it on. B comma D, likewise, is covering the second query, but not the first. And if you had a bigger composite index of B comma C comma D, that will actually cover both your queries. So how do you build a covering index? Well, what you need to do is you need to add every field from the select, not just the where clause. So if I have a query of select C comma D from foo, where A is equal to 10 and B is equal to 100, a mistake a lot of people make is they really just follow the first rule that I talked about. They just focus on the where clause, optimize for that, and then they're done. But that's not enough. They don't make that. And if you just follow the first rule, you'll be like, oh, let me add an index on A comma B, and you just go on your way. But that's not enough. What you actually need to do is you're still going to have point queries to retrieve those values of C and D. You need to not just add what you see in the where clause, you need to add what you also see in the select clause. So you need to add C and D. So really, you want your index to be A, B, C, D. That includes all your referenced fields. You place A and B at the beginning to take advantage of rule 1, and you're good. And I'm sure people that are thinking, about MongoDB, it was like, well, MongoDB schemaless, I don't have the nice, column definition to be able to know what all my queries are going to be looking like. And for MongoDB, I would think, I don't want to argue because I'm not, running it, but I would think for MongoDB, it's a little more challenging to build a covering index because a covering index sort of implies a schema. I know what my queries are. I know what my fields or columns are. I'm going to build an index around that. And MongoDB is saying, well, you're schemaless. You might be querying fields you don't know about tomorrow. And we'll get into a little bit of that sort of later on. So I just want to point out that, yes, I believe in MongoDB this is a little more challenging than it would be in something that's relational like MySQL. But the fact still remains, you want your index to be covering, you need to include all your columns. Now, what if the primary key matches the where clause? Now, what I'm about to say here it applies to TokuMX, TokuDB, and InnoDB. It does not apply to MongoDB because MongoDB doesn't have a primary key, and it doesn't apply to MyISAM because MyISAM does not store the data with the primary key. But for Tokutext products and InnoDB, if the primary key matches the where clause, where you have a primary key of B and an auto increment, I added the auto increment so you ensure uniqueness. As we know, primary keys must be unique. Well, the query is going to do a range query on the primary dictionary. And because only one dictionary is accessed, that's going to be in sequential order. This is fast. And so an important note here is the primary key covers all queries. So if your sort order matches the where clause, your problems are solved. And this gets to the concept of what I'm sure people have heard is that things like InnoDB and TokuDB and TokuMX, their primary key is a clustering key. So what if the primary key doesn't match the where clause? Well, ideally, you should be able to declare your secondary indexes to carry all your fields, but for databases, they don't quite let you do this, except TokuMX and TokuDB. So what I want to do here now is I want to talk just briefly about the value of a clustering index. What a clustering index does in TokuMX and TokuDB is it is going to take all of your data and it's going to put it with the secondary index. It's going to have another copy of your data in the secondary index. So all the work we were talking about, like before, about worrying about point queries into the main dictionary, that no longer becomes necessary. In TokuDB, you want to define a clustering index. You just define the clustering keyword. In TokuMX, you could add the attribute clustering1 to a defined index, and it will be when you define the index. You have to do it when at the point of defining the index, and the index will be clustering. So let's just talk about clustering keys in action here. Let's talk about them in a MySQL world, and I'm going to tie a bit of it into the MongoDB world. So suppose, in MySQL, I have a schema. I know what my columns are, and I know I'm going to be doing a bunch of these queries. I'm going to be select some C where B is less than 100, some D where B is greater than 200, or select C and E where B is equal to 1,000. So how do I go about, designing covering indexes for these? Because I just made the argument covering indexes improve the speed of your queries by so much. What do? All right, well, BC is going to take care of the first query. BD is going to take care of the second. BCE is going to take care of the first and third, but not the second. And BCDE is going to take care of all three queries. Well, I don't know about you guys, but that was a little exhausting for me. And so that required a lot of analysis for the queries. Now let's think about this in a MongoDB world. Like in the MySQL world, I'm lucky. I know I only have columns A, B, C, D, E. In MongoDB, who knows what my documents look like? Who knows what my fields look like? So in fact, in MongoDB, designing a covering index may just be impossible if your indexes are rich enough. And this is where clustering keys really benefit. In the MySQL world, it makes your analysis easier. You have just set a clustering key on B and you're done. In the MongoDB world, it allows you to take care of queries that are just completely unforeseen. So if you guys want to go back to your schemas later, if you notice in your MySQL schemas, you have a key of AB, AC, AD, AE, and whatnot. Generally, when I see that in the wild, I start thinking, I bet a clustering key on just A would benefit that. So the key takeaway I sort of want to drive point home on what the clustering keys do is it just lets you focus on the where clause. It takes this second rule really out of the equation, focus on reducing the rows retrieve, your point queries will be eliminated, and your queries are just going to be fast. Now, recall in the middle of rule 1, I talked about an index merge and how that was a possibility. And now I sort of want to bring that, back. We had the query select some C from foo where B is equal to 10 and A is less than 150. And once again, we had 200,000 rows where A is less than 150, 100,000 where B is equal to 10, and 1,000 where they both match. So what if we used key of AB and we merged the results? Well, what would happen is, what would be your merge plan? Scan 200,000 rows in a range query to see where A is less than 150. You scan 100,000 rows to see where B is 10. You merge the results and you find the 1,000 row identifiers that match the query. So what the index merge is doing is it's not reducing the rows analyzed to answer the query. What it's doing is it's reducing the cost of each row analyzed by only inducing point queries on the 1,000 rows that match and not the 100K or 200K if you'd use just one index. And this is actually better than no indexes. Your scans got better, your point queries got a lot less compared to not merging. If you use a clustering key on A, well, then you're just going to scan your 200,000 rows where A is less than 150. The resulting rows will already have the value of B in there where B is equal to 10. And you could just pluck out those C values from the remaining 1,000 rows. And once again, you get no point queries. But if you really want to put the rules of the first two that we put together, for this query, what I would do is I would have a clustering key on B, comma A. That just wins all around. So this takes us to the conclusion of rule number 2. Once again, you want to avoid point queries. You want to make sure your index covers the query. And when you can, you want to use clustering indexes. And this brings us to rule 3. Rule 3, so avoid sorting. Now, The simple selects that we've been talking about so far really require no post-processing. If I have select star from foo where b is equal to 100, I just get the data, give it back to the user. Done. But if I need to group by or order by, then I might have to sort the data. Wow, sorry about that. If I have a group by or order by, I might have to sort data. So complex queries can have post-processing. And what we can do is, if we don't want to do this sort work during query time, we could actually use index selection to avoid the sorting step. So if I have a query of select count C from foo, and I suppose we have two queries, select count C from foo and select count C from foo, group by B, order by B. Well, the query plan for one's pretty simple. While you're doing a table, assume you have no indexes. While you're doing a table scan, you just count the rows for C. You're done. But for query 2, it's a little more complicated. As you're scanning the table, you have to write the data to a temporary file. You have to sort that temporary file by B. Then you need to rescan the sorted data and count the rows with C for each B. And it's this writing to a temporary file and sort and rescan. That's sort of the extra work that you would do on top of what you did for the first query. And that could be expensive. And we could use indexing to avoid some of that work at query time. So how do we go about doing it? Well, if we had a key of B comma C, well, first off, notice we've added all the needed fields, so the index is covering, so that's fast. And by sorting first on B, we're going to avoid the sort, so that's fast. So the take home here is, by having an index here that starts with B, we were able to save the time of the group by and the order by on query time by avoiding the sorting. So really, to sum up, this is, I think, the simpler of the three rules. Use indexes where you can to pre-sort the data for order by and group by for your queries. Okay, so this discusses the three rules. Now what I want to do is I just want to run through some simple examples. I want to put this all together, and let's actually put a little bit of practice here. So first example, select count star from foo where C is equal to 5, group by B. Well, this one we're going to want a key of C comma B. First have C to limit the rows retrieved using rule 1. Then you have the remaining rows sorted by B to avoid the sort of rule 3. And because the remaining rows will be sorted by B, the remaining rows are going to be sorted by B because you had an equality test. See, this is also a good example of really why an equality test is pretty nice. Example 2. Select some D from foo where C is equal to 100, group by B. This is similar, but we have to add that column of B at the end. Once again, you have C to limit the rows retrieved. Then you have the remaining rows sorted on B, so you take advantage of rule 3. But then to make sure that the index is covering the query, you're going to want to add the column D. And there you go. Now, sometimes, unfortunately, there is no clear answer, and the best index is data dependent. So you take this query, select count star from foo where C is less than 100, group by B. Now, what can you do here? You can have an index of C comma B, or you could have an index of B comma C. Let's see how these compare. Well, if I have a query plan of C comma B, what's this going to do? This is going to filter the rows where C is less than 100, but the problem is you're not going to have your remaining rows sorted by B. And that's because, they're sorted on C. Maybe the rows where C is 99 are sorted within each other, and where C's 98 are sorted within each other, but the overall set is not going to be sorted overall by B. And therefore, you're still going to need to do the post-processing sorting. And this is also another example of really, if you can have equality checks in your where clause, go for it. Equality checks are wonderful. If C was an equality check here, instead of being a less than, then it would basically be the equivalent to the first query I gave in the example, and you'd be done. So I guess a sidebar to what I'm saying here is also, equality checks on where clauses are very nice. The other query plan of where you have B comma C, well, you're sorted by B, so rule 3 is covered. But the rows where C is greater than or equal to 100 are also processed, so you're not taking advantage of rule 1. Now, which is better? And that depends on the data. If there are many rows where C is greater than or equal to 100, you're going to save time by not retrieving these useless rows, so use CB. But if there aren't so many rows where C is greater than or equal to 100, the time to execute the query is dominated by sorting, so use BC. So the point is, the rules of thumb help, but often, you can't think of this as a recipe. You got to really think about your queries and indexes and sort of see what fits best. Now, and sort of finally, I need to make the point is, why do we not just load up on indexes? Well, the issue could be indexes take more space. Each index adds storage requirements, but what can you do? Well, the nice thing is TokuDB and TokuMX use compression. We've seen numbers from 5 to 15x, and the TokuMX realm, I think I saw a tweet the other day where somebody got like 30 to 1 compression on their tables. He was getting like, I don't remember what he was getting on his indexes, but TokuDB and TokuMX compression will really help with the storage requirements for indexing. Performance, sort of where TokuDB and TokuMX's performance shines, where B trees, while they're fast for some indexing tasks, if you ever hear keep your indexes in memory, keep your working set in memory, use a rightmost insertion pattern. These are all basically things that they tell you to make sure that your B tree indexing is fast. But if it gets really big, it can be really slow, and then your indexing starts to hurt more than it helps. And the nice thing about fractal tree indexes, which is what TokuDB and TokuMX use, is that it's fast at all kinds of indexing. Random keys, large keys, wide keys, etc. So the nice thing that it does is it sort of puts it puts the concern about write performance and space to the side, and you can really focus on what this talk was saying is, focus on analyzing your queries and designing the indexes for that. And the last caveat is, as you may know, is everything that I've been talking about here is that range queries are fast, point queries are slow. Well, this is only true as long as, your trees don't get fragmented. You might be aware that, in MySQL, you're told once in a while you have to run optimized table. It's because of B tree fragments. In MongoDB, you're told once in a while, run compact on your databases, run compact. Once again, this is because B trees fragment. They get slow for range queries, your performance starts tanking, and sort of the rules that you were seeing earlier don't apply as well. And in order to do that, well, you need to run optimized table or compact, or with fractal tree indexing, this is not an issue because fractal trees don't fragment. And so that concludes the webinar. I'd like to thank everyone for attending and listening to the presentation. I'm now available for any questions. If you want to download TokuMX or TokuDB, please visit tokutech.com/downloads. Once again, it's completely open source. So there's a free community version. You can just download. You can download the community version and just start using it right out of the gate. And please register for access to premium content and other goodies. All right, and with that, now I am going to be looking into I'm going to be looking into questions. I'm going to scroll up first at the top. All right, I see a bunch of confirmations that my audio was good, excellent. I see what's a point query, I believe I answered that. I see a question, I assume your use of the term clustering is different and distinct from the traditional concept of clustered indexes. I don't believe it is different. The point of it's the clustered index. I'm not talking about, clusters the way you have, multi-machine clusters. I'm talking about, okay, I see. I see that now. I was thinking of the old SQL Server days. Basically, a clustering index is an index that stores all the data with your key. Generally, for InnoDB, the primary key is known as a clustering index. You do a search for InnoDB clustering index, you'll see it on a primary key. MongoDB and MyISAM do not have any clustering indexes. And TokuMX and TokuDB allow you to have multiple clustering indexes because they're very cool. I see the next question is, can you talk a little bit about how MongoDB manages indexes in a replica set? It is very expensive versus It is very expensive versus a single instance. Oh, it's a question. It's actually no different. So MongoDB replication sort of just talks about rows going over the wire. Like you insert a row, you update a row, you delete a row. It sort of copies that over to your secondaries as well. So what actual secondary indexes exist don't matter. So as far as managing the indexes, there's no difference between a replica set versus a single instance. Um, I arrived at how can I see the whole thing? I believe that this is being recorded and will be available online. If you registered for the webinar, I think you'll get an email saying how you can watch it again. Can I recommend some additional reading about indexes? I take a look at some of the blog posts. I take a look at some of the blog posts that we've had. As far as books and whatnot go, I don't know. There's a question, can we get the PowerPoint? I don't know. I imagine it. I guess it would be available, but yes, we'll be able to find this. Like this presentation can be found online. So, all right. Are there any other questions? Waiting. All right. Looks like that's it. So yes. Once again, I'm seeing slides and video will be available on our website after the webinar. Oh no, I don't have the flu. I just had a cough. So, I see some other questions. If I have a system with a large count of queries, how can I determine the suitable indexes for the table? I mean, this is sort of where the problem analysis comes in, where you've got, you've like indexes are only good for queries. So you sort of got to take a look at, is there a pattern in your queries? Is the where clause at least? Is the where clause matching a lot of them, or are they just completely ad hoc? Like if you can literally query any column in any way, then sometimes table scans might be necessary. You just can't index it in all the ways that you want to. So really, unfortunately, it's about it's just about that's where the problem analysis comes. There are no recipes. Next question: can you talk about delete data and indexes? Delete data is you can think of deletions as just another type of writes, and they have the same challenges as writes. If you're doing random writes into a B tree, your data grows large, it could be an issue. They tell you for B trees, keep your working set in memory, keep your indexes in memory. For fractal trees, this isn't necessary. So as far as deleting of data goes, it's really no different than inserting. Like the data will be reclaimed. Sometimes, deleting data, like if you delete it from random places, it's like inserting it to random places where you might get fragmentation. But really the same things apply. Is there any benchmark comparison data against other MySQL database engine? I don't understand that question. So a benchmark of what? We have several benchmarks on our website of TokuDB compared to InnoDB in several areas. We have several benchmarks of TokuMX compared to MongoDB, and both heavy write workloads, mixed read write workloads, etc. So I think tokutech.com maybe/benchmarks. I'm pretty sure a Google search of it will find benchmarks on our website. Just do TokuMX, MongoDB benchmark, etc. Would the clustering index help delete data faster? A good way to think about deletions and updates, actually deletions and updates go together, is deletions and updates are really a combination of queries and writes. If I have an update statement, update foo, set b equal to b plus 1, where a is equal to 10, it comes in two parts. You first do a query to find the rows that require updating, and then you do the writes to apply the actual updates. So because a clustering index helps queries, it can absolutely help writes. It can absolutely help deletes. But once again, you got to remember a clustering index has a little more maintenance cost. For fractal trees, they're not that bad. So the question is, will that clustering index really help the query portion? And for several delete operations that I've seen, the answer is absolutely. It'll help big time. All right. Okay, I'm enforced to remove the sorting from the queries, or can I keep them and have another way to accelerate the query, especially if the sorting can be on any column in the DB? Um, Unfortunately, let me just think on that for a second. I mean, indexes sort, so if you want to avoid the sorting, you got to have it at the end. Like, the problem is that I've sort of just given guidelines of sort of taking a query and matching an index to it. But as we know, people's workloads aren't going to be a single query and, a single index and you're done. You've got a combination of queries and you've got a combination, and you can only afford a combination of indexes. Like, regardless, even no matter how great TokuDB and TokuMX is at indexing, and it's way better than what anything else you'll see out there, there's still going to be a limit, and you sort of need to decide what's best given the importance of your workload. All right, the next question is, can you differentiate the strengths of TokuMX and TokuDB? As far so differentiating between, do you mean compared to each other or compared to MongoDB and MySQL So I don't know if the person asking that question could clarify, that'd be great. What would be a good index for time sorted data? Just add the time as the first element of all indexes, or is there a better way? I'd say for that, for time, well, you see, time sorted data means that you have an index on time. Otherwise, it wouldn't necessarily be sorted on time. So really the question is, what are your queries? And does it make sense to have your data sorted by time? Because time is sequential, because time is sequential, it's going to be, fast for B trees to write, but it doesn't necessarily mean that's going to be the best index for your queries. All right, so the last question, differentiate the strengths of TokuMX. All right, let's talk about TokuMX versus MongoDB. So what I'd like to say, 6 big benefits of TokuMX over MongoDB. And I'll go over them sort of in no particular order. Number 1, compression. So whether you're running on SSD or running on a hard disk, TokuMX compresses very well compared to MongoDB. That is just always a given. We were probably always going to win on compression. I saw a tweet the other, and it depends on how compressible your data is. So if you're storing JPEGs in Mongo, that's not going to compress well. But if you have a lot of repeatable data, that's going to compress great. Second one, write performance. As I was saying, in MongoDB, you're stressed. Keep your indexes in memory. Keep your working set in memory. Don't let your indexes get too big. And the reason for that is because write performance suffers. Our write performance doesn't suffer, so you can actually design the indexes you want to design and not worry if those indexes flow out of memory. So it actually makes the concepts that I talked about in this talk a lot easier to apply because you're not constantly coming up against the penalty that you would get with writes. Another benefit is no fragmentation. We've deprecated compact. Another benefit of TokuMX over MongoDB is we do not have a database level lock. We have document level locking, so the parallelism is a lot better, especially on single collections or single databases. We have benchmarks on our website of mixed read-write workloads where we perform on out-of-memory workloads. I think it was something like 15 to 20x better. It's just a benchmark, though. And on an in-memory workload, it was mixed read-write. We were 4 times better. And the reason for that, and we have a customer with a press release that I believe they said they just out of the box without any changes to their application 2 times better. And the gist of the reason for that is we have document level locking. MongoDB has database level locking. There's a big benefit there. Another one is on non-sharded clusters, we've implemented transactions and MVCC. So in MongoDB, you sort of do a long query. You sort of got to cross your fingers that that writes that come at the same time don't mess with the consistency of your results. With TokuMX, all your queries are on a snapshot of the data. It's just like it would be on InnoDB or TokuDB. Multi-statement, every statement is a transaction. You can actually batch your writes together. I actually have a few good blog posts on transactions in TokuMX and the benefits they bring. If you sort of just Google TokuMX and TokuMX transaction MongoDB, I think you'll find them. You can batch your writes a lot better. And we've brought multi-document transactions. And I think lastly, as I said, there are a whole bunch of benefits. Lastly, clustering indexes. I think clustering indexes in a SQL world where you have your columns well defined, yeah, they could probably help. They'd be pretty convenient. Clustering indexes to eliminate point queries in a NoSQL world where you're not relational and your documents can have any form, I think that's a lot more power. I think that could be a lot more powerful, and that can really ease index design. So I think clustering indexes in TokuMX is a big deal. I know that was a bit of a long answer, but hopefully that's the nice, short, summary on the advantages of TokuMX over MongoDB. All right. Any other questions? Well, I guess I'll wait 30 seconds to see if anybody else types. Okay, I'd like to thank everybody for attending the webinar. I don't see any more questions, so I guess we'll wrap it up. So once again, you guys just visit our website. I'm sure you can contact us with any questions, and thank you.